Hello, we are back, jumping back into C Programming, a Modern Approach, second edition by K and King. Today we're going to be reading Chapter 4, Expressions. All right, so I hope you guys are ready to go for today. Let's just jump right on in to today's reading. I'm super excited to get started today. Keep the grind going. This is going to be Chapter 4 of C Programming, a Modern Approach, second edition by K and King. Chapter 4, Expressions. The notes can be found on my GitHub, linked down in the description below. This is going to be the condensed version. If you'd like to watch the full live stream, feel free to join me almost every single day around 7 p.m. PST as I teach myself computer science and programming from scratch. Thank you guys so much for being here. Let's go ahead and jump right on into C Programming, a Modern Approach, second edition, Chapter 4. Chapter 4, Expressions. One does not learn computing by using a hand calculator, but one can forget arithmetic. One of C's distinguishing characteristics is its emphasis on expressions, formulas that show how to compute a value rather than a statement. The simplest expressions are variables and constants. A variable represents a value to be computed as the program runs. A constant represents a value that doesn't change. More complicated expressions apply operators to operands, which are themselves expressions. In the expression a plus b times c, the plus operator is applied to the operands a and parentheses b star c parentheses, both of which are expressions in their own right. Operators are the basic tools for building expressions, and C has an unusually rich collection of them. To start off, C provides the rudimentary operators that are found in most programming languages. Arithmetic operators including addition, subtraction, multiplication, and division. Relational operators to perform comparison such as I is greater than 0, logical operators to build conditions such as I is greater than 0 and I is less than 10. But C doesn't stop there. It goes on to provide dozens of other operators. There are so many operators, in fact, that we'll need to introduce them gradually over the first 20 chapters of this book. Mastering so many operators can be a chore, but it's essential to becoming a proficient at C. In this chapter, we'll cover some of C's most fundamental operators, the arithmetic operators, section 4.1, the assignment operators in section 4.2, and the increment and decrement operators, section 4.3. Section 4.1 also explains operator precedence and associativity, which are important for expressions that contain more than one operator. Section 4.4 describes how C expressions are evaluated. And finally, section 4.5 introduces the expression statement, an unusual feature that allows any expression to serve as a statement. 4.1 Arithmetic operators. The arithmetic operators, the operators that perform addition, subtraction, multiplication, and division, are the workhorses of many programming languages, including C. Table 4.1 shows C's arithmetic operators. The additive and multiplicative operators are said to be binary because they require two operands. The unary operators require one operand. I equals plus 1. Plus is used as a unary operator. J equals minus I, minus used as a unary operator. The unary plus operator does nothing. In fact, it doesn't even exist in K and RC. It's used primarily to emphasize that a numeric constant is positive. The binary operators probably look familiar. The only one that might not is the percent, the remainder operator. The value of I percent j is the remainder when I is divided by j. For example, the value of 10 modulo 3 is 1. The value of 12 modulo 4 is 0. The binary operators in table 4.1, with the exception of modulo, allow either integer or floating point operands, with mixing allowed. When int and float operands are mixed, the result has a type float. Thus, 9 plus 2.5 float has a value of 11.5, and 6.7 float divided by 2 has a value of 3.35. The divide and modulo operators require special care. The divide operator can produce surprising results. When both of its operands are integers, the divide operator truncates the result by dropping the fractional part. Thus, the value of 1/2 is 0, not 0.5. The modulo operator requires integer operands. If either operand is not an integer, the program won't compile. Using 0 as the right operand of either Division or modulo causes undefined behavior. Describing the result when division and modulo are used with negative operands is tricky. The C89 standard states that if either operand is negative, the result of a division can be rounded either up or down. For example, the value of negative 9 divided by 7 could be either negative 1 or negative 2. If I or j is negative, the sign of I modulo j in C89 depends on the implementation. For example, the value of negative 9 modulo 7 could be either negative 2 or 5. In C99, on the other hand, the result of a division is always truncated toward 0. So negative 9 divided by 7, the value is negative 1. And the value of I modulo j has the same sign as I. Hence, the value of negative 9 modulo 7 is negative 2. Implementation defined behavior. The term implementation defined will arise often enough that it's worth taking a moment to discuss it. The C standard deliberately leaves parts of the language unspecified, with the understanding that an implementation, the software needed to compile, link, and execute programs on a particular platform, will fill in the details. As a result, the behavior of the program may vary somewhat from one implementation to another. The behavior of the division and modulo operators for negative operands in C89 is an example of the implementation defined behavior. Leaving parts of the language unspecified may seem odd or even dangerous, but it reflects C's philosophy. One of the language's goals is efficiency, which often means matching the way that hardware behaves. Some CPUs yield negative 1 when negative 9 is divided by 7, while others produce negative 2. The C89 standard simply reflects this fact of life. It's best to avoid writing programs that depend on implementation-defined behavior. If that's not possible, at least check the manual carefully. The C standard requires that implementation-defined behavior be documented. Operator precedence and associativity. When an expression contains more than one operator, its interpretation may not be immediately clear. For example, does I plus j times k mean add I and j, then multiply the result by k? Or does it mean multiply j and k, then add I? One solution to this problem is to add parentheses, writing either I plus j times k or I plus parentheses j times k. As a general rule, C allows the use of parentheses for grouping in all expressions. What if we don't use parentheses though? Will the compiler interpret I plus j times k as parentheses I plus j close parentheses times k, or I plus parentheses j times k close parentheses? Like many other languages, C uses operator precedence rules to resolve this potential ambiguity. The arithmetic operators have the following relative precedence: highest order, plus minus unary, multiplication, division, modulo, and then lowest are plus minus binary. Operators listed on the same line, such as plus and minus, have equal precedence. When two or more operators appear in the same expression, we can determine how the compiler will interpret the expression repeatedly, putting parentheses around sub-expressions, starting with high precedence operators and working down to low precedence operators. The following example illustrates the results. No parentheses in this expression, I plus j times k, is equivalent to this, where we have order of operations taking place, where the multiplication happens before the addition. Negative I times negative j is equivalent to parenthesis negative I by itself times parenthesis negative j by itself. Positive I plus j divided by k is equivalent to positive I within itself plus the operand j divided by k. Operator precedence rules alone aren't enough when an expression contains two or more operators at the same level of precedence. In this situation, the associativity of the operators comes into play. An operator is said to be left associative if it groups from left to right. The binary arithmetic operators, multiplication, division, modulo, plus, and minus, are all left associative, so I minus j minus k equals 2, combining the first one first into a single operand, sub-operand we'll say. And then this expression, I times j divided by k, is equivalent to making the first sub-expression wrap around that operand of equal precedence. An operator is right associative if it's groups from right to left. The unary arithmetic operators plus and minus are both right associative, so plus minus I is equivalent to minus parentheses plus I parentheses, which ultimately makes this a negative value if I is positive in itself already, which it is indicated by this value here. Precedence and associativity rules are important in many languages, but especially so in C. However, C has so many operators, almost 50, that few programmers bother to memorize that precedence and associativity rules. Instead, they consult a table of operators when in doubt, or just use plenty of parentheses. Program computing a UPC check digit. For a number of years, manufacturers of goods sold in US and Canadian stores have put a barcode on each product. This code, known as a Universal Product Code, or UPC, identifies both the manufacturer and the product. Each barcode represents a 12-digit number, which is usually printed underneath the bars. For example, the following barcode comes from a package of Stouffer's French bread pepperoni pizza. The digits 0, 13800, 15173, and 5 appear underneath the barcode. The first digit identifies the type of the item, 0 or 7 for most items, 2 for items that must be weighed, 3 for drugs and health-related merchandise, and 5 for coupons. The first group of 5 digits identifies the manufacturer. 13800 is the code for Nestle USA Frozen Food Division. The second group of 5 digits identifies the product, including package size. The final digit is a check digit whose only purpose is to help identify an error in the preceding digits. If the UPC is scanned incorrectly, the first 11 digits probably won't be consistent with the last digit, and the store scanner will reject the entire code. Here's one method of computing the check digit. Add the first, third, fifth, 7th, 9th, and 11th digits. Add the second, fourth, 6th, 8th, and 10th digits. Multiply the first sum by 3 and add it to the second sum. Subtract 1 from the total. Compute the remainder when the adjusted total is divided by 10. Subtract the remainder from 9. Using the Stouffer's example, we get 0 plus 3 plus 0 plus 1 plus 1 plus 3 equals to 8 for the first sum, and 1 plus 8 plus 0 plus 5 plus 7 equals to 21 for the second sum. Multiplying the first sum by 3 and adding the second yields 45. Subtracting 1 gives 44. The remainder upon dividing by 10 is 4. When the remainder is subtracted from 9, the result is 5. Here are a couple of other UPCs in case you want to try your hand at computing the check digit. Raiding the kitchen cabinets for the answer is not allowed. Here's Jif creamy peanut butter, Ocean Spray jellied cranberry sauce. The answers appear at the bottom of the page. Let's write a program that calculates the check digit for an arbitrary UPC. We'll ask the user to enter the first 11 digits of the UPC, then we'll display the corresponding check digit to avoid confusion. We'll ask the user to enter the number in 3 parts: the single digit at the left, the first group of the 5 digits, and the second group of 5 digits. Here's what a session of the program will look like. Enter the first single digit, 0. Enter the first group of 5 digits, 13800. Enter the second group of 5 digits, 15173. Check digit is 5. Instead of reading each group as a 5-digit number, we'll read it as a 5 one-digit numbers. Reading the numbers as single digits is more convenient. Also, we won't have to worry that one of the 5-digit numbers is too large to store in an int variable. Some old compilers limit the maximum value of an int variable to 32,767. To read single digits, we'll use scanf with the %1d conversion specification, which matches a 1-digit integer. So we are going to include standard I/O in this code. We're going to have a main function where we're going to define a d, I1, 2, 3, 4, 5, J1, 2, 3, 4, 5. First sum, second sum, and total, all with our ints. Printf, enter the first single digit. We are going to scanf for a single digit and save that in D's pointer. We're going to printf, enter the first group of 5 digits, and we're going to scanf for 5 single digits and save those in I, 1 through 5 pointers. Printf, enter second group of 5 digits. We do the same thing of 5 1 integer conversion specifiers with the J 1 through 5 pointer integer declarations. We then compute a first sum, which is D plus I, 2, 4, J 1, 3, and 5. Second sum, I, 1, 3, 5, J 2, J 4. Total is 3 times first sum plus second sum. And we say printf, check digit is the inserted integer value, \n for a new line, and we're going to insert into there the expression 9 minus the total minus 1 modulo by 10 and return 0. Note that the expression 9 minus parenthesis total minus 1 parenthesis modulo 10 parenthesis could have been written as 9 minus total minus 1 modulo 10 with parentheses around total and minus 1 in the middle. But the extra set of parentheses makes it easier to understand. You're going to do this one, then take that value and do this, and then take that whole value and do 9 minus that whole thing, right? Just order of operations, if you are familiar with those from algebra. Cool, that was 4.1, assignment operators. Once the value of an expression has been computed, we'll often need to store it in a variable for later use. C's equals to, simple assignment operator, is used for that purpose. For updating a value already stored in a variable, C provides an assortment of compound assignment operators. Simple assignment. The effect of the assignment V equals to E is to evaluate the expression E and copy its value into V. As the following example shows, E can be a constant, a variable, or a more complicated expression. So here we have I is equal to 5. I is now 5. We say J is equal to I. J is now 5. We say K equals to 10 times I plus J. K is now 55. 5 times 10, which is 5 plus 5, 55. If V and E don't have the same type, then the value of E is converted to the type of V as the assignment takes place. So if we have int I and float F, and I is equal to 7.299F, I is now converted to 72 from 72.99. Got truncated down into the integer form. We say F is equal to 136. F is now 136.0. We'll return to this topic of type conversion later. In many programming languages, assignment is a statement. In C, however, assignment is an operator just like plus. In other words, the act of assignment produces a result just as adding two numbers produces a result. The value of an assignment V equals E is the value of V after the assignment. Thus, the value of I equals to 72.99F is 72, not 72.99. Side effects. We don't normally expect operators to modify their operands since operators in the mathematics don't. Writing I plus J doesn't modify either I or J, it simply computes the resulting of adding I and J. Most C operators don't modify their operands, but some do. We say that these operators have side effects since they do more than just compute a value. The simple assignment operator is the first operator we've seen that has side effects. It modifies its left operand. Evaluating the expression I equals 0 produces the result 0, and as a side effect assigns 0 to I. Since assignment is an operator, several assignments can be chained together. I equals J, which equals K, which equals 0. The equals operator is right associative, so the assignment is equivalent to I equals to parenthesis J equal to parenthesis K equal to 0 parenthesis parenthesis. The effect is to assign 0 to first K, then to J, and finally to I. Watch out for unexpected results in chain assignment as a result of type conversion. Int I float F, F equals to I, which equals to 33.3F. I is assigned the value of 33 as we note above in our notes. Then F is assigned to 33.0, not 33.3 as you might think, because F is receiving the value of I, which I truncates 33.3 down to 33 because of its int declaration. In general, an assignment of the form V equals E is allowed wherever a value of type V would be permitted. In the following example, the expression J equals to I copies I to J. The new value of J is then added to 1, producing the new value of K. I is equal to 1, K is equal to 1 plus J equals to I. Printf, integer, space, new line, and insert I, J, and K. We set J equal to I in this K declaration, so J is equal to 1. We then add 1 to J to assign that to K, and so K becomes 2. So we print out 1, 1, and 2. Using the assignment operator in this fashion usually isn't a good idea. For one thing, embedded assignments can make programs hard to read. They can also be a source of subtle bugs, as we'll see in section 4.4. L values. Most C operators allow their operands to be variables, constants, or expressions containing other operators. The assignment operator, however, requires an L value as its left operand. An L value, pronounced L value, represents an object stored in computer memory, not a constant or the result of a computation. Variables are L values. Expressions such as 10 or 2 times I are not. At this point, variables are the only L values that we know about. Other kinds of L values will appear in later chapters. Since the assignment operator requires an L value as its left operand, it's illegal to put any other kind of expression on the left side of an assignment expression. I is equal to 12 is wrong. I plus j is equal to 0 is wrong. Negative I is equal to j is wrong. The compiler will detect errors of this nature, and you'll get an error message such as invalid L value in assignment. Assignments that use the old value of a variable to compute its new value are common in C programs. The following statement, for example, adds 2 to the value stored in I equals to I plus 2. C's compound assignment operators allow us to shorten the statement and others like it. Using the plus equals operator, we simply write I plus equals to 2, which is the same as saying I equals to I plus 2. The plus equals operator adds the value of the right operand to the value of the right operand to the variable on the left. There are 9 other compound assignment operators, including the following: minus equals to, multiply equals, divide equals, modulo equals. We'll cover the remaining compound assignment operators in a later chapter. All compound assignment operators work in much the same way. V plus equals to E adds V to E, storing the result in V. Same thing for minus, but it says subtraction. Same thing for V, but for multiplication. Same thing for division, but this is division. And then modulo, we just modulo computes the remainder when V is divided by E and stores the resulting in V. Note that I've been careful not to say that V plus equals E is equivalent to V equals V plus E. One problem is operator precedence. I multiply equals j plus k isn't the same as I equals to I times j plus k. There are also rare cases in which V plus equals to E differs from V equals to V plus E because V itself has a side effect. Similar remarks apply to the other compound assignment operators. When using the compound assignment operator, be careful not to switch the 2 characters that make up the operator. Switching the characters may yield an expression that is acceptable to the compiler but does not have the intended meaning. For example, if you want to write I plus equals j, but typed I equals plus j instead, the program will still compile. Unfortunately, the latter expression is equivalent to I equals to parentheses plus j, which merely copies the value of j positively into I. The compound assignment operators have the same properties as the equals to operator or simple assignment. In particular, they're right associative, so the statement I plus equals j plus equals k means that we're going to assign j to in place add on with k on top of it, and then do that value on top of I. 4.3 Increment and decrement operators. 2 of the most common operations on a variable are incrementing, adding 1, and decrementing, subtracting 1. We can of course accomplish these tasks by writing I equals to I plus 1 or j equals to j plus 1. The compound assignment operators allow us to condense the statement a bit to I plus equals 1 or j minus equals 1. But C allows increments and decrements to be shorthanded even further using the plus plus increment and minus minus decrement operators. At first glance, the increment and decrement operators are sufficient itself. Plus plus adds 1 to the operator, whereas minus minus subtracts 1. Unfortunately, this simplicity is misleading. The increment and decrement operators can be tricky to use. One complication is that plus plus and minus minus can be used as a prefix operators. Plus plus I and minus minus I, for example, or postfix operators, I plus plus or I minus minus. The correctness of a program may hinge on picking the proper version. Another complication is that, like the assignment operators, plus plus and minus minus have side effects. They modify the values of their operands. Evaluating the expression plus plus I, a pre-increment, yields I plus 1, and as a side effect, increments 1. Another complication is that, like the assignment operators, plus plus and minus minus have side effects. They modify the values of their operands. Evaluating the expression plus plus I, a pre-increment, yields I plus 1, and as a side effect, increments I. I equals to 1, printf, I is %d \n plus plus I, prints I is 2. Printf, I is %d \n I, prints I is 2. Evaluating the expression I plus plus, a post-increment produces the result I, but causes I to be incremented afterward. I equals to 1. Printf, I is this, we call I plus plus. I is 1. Print f, I is here, and insert I now, and I is 2. The first printf shows the original value of I before it's incremented. The second printf shows the new value as these examples illustrate. Plus plus I means increment I immediately, while I plus plus means use the old value of I for now, but increment it later. How much later? The C standard doesn't specify a precise time, but it's safe to assume that I will be incremented before the next statement is executed. The minus minus operator has similar properties. I equals to 1, printf, I is, and then we're going to do minus, so this is going to be 0. Perfect. Now we have I is 1, and we're going to do it later. Well, this one's going to print out just 1, and this one's going to print out 0. Perfect. When plus plus or minus minus is used more than once in the same expression, the results can often be hard to understand. Consider the following statements. I is equal to 1 and j is equal to 2. We're going to call k being equal to plus plus I plus j plus plus. So let's think about what's happening here. I is being incremented immediately in this expression, so we're going to increase I to 2. So this value is 2. J is being incremented after the expression happens, so we're going to use 2 at this point in time. And so this will be 2 plus 2, which I think will be 4. What are the values of I, j, and k after these statements are executed? Since I is incremented before its value is used, but j is incremented after it is used, the last statement is equivalent to I equals to I plus 1, k equals to I plus j equals to j plus 1. So the final values of I, j, and k are 2, 3, and 4, respectively. In contrast, executing the statements, I equals to 1, j equals to 2, and k equals to I plus j plus will give us 3 for k. Will give I, j, and k values of 2, 3, and 3, respectively. For the record, the postfix versions of plus plus and minus minus have higher precedence than unary plus and minus and are left associative. The prefix versions have the same precedence as unary plus and minus and are right associative. Expression evaluation. The table 4.2 summarizes the operators we've seen so far. Appendix A has a similar table that shows all operators. The first column shows the precedence of each. So we have increment and decrement postfix, which has top precedence and left associativity. Second precedence is increment, decrement prefix, unary plus, unary minus, right? Third precedence is multiplicative, left. Fourth precedence is additive, left. And fifth precedence is assignment, right, associative. The first column shows the precedence of each operator relative to the other operators in the table. The highest precedence is 1, the lowest is 5. The last column shows the associativity of each operator. Table 4.2, or its larger cousin in Appendix A, has a variety of uses. Let's look at one of these. Suppose that we run across a complicated expression such as A equals to B plus equals to C plus plus minus D plus minus minus E divided by minus F. This expression would be easier to understand if there were parentheses to show how the expression is constructed from sub-expressions. With the help of Table 4.2, adding parentheses to an expression is easy. After examining the expression to find the operator with the highest precedence, we put parentheses around the operator and its operands, indicating that it should be treated as a single operand from that point onwards. So the operator with the highest precedence would be the postfix C++ here. We then repeat the process until the expression is fully parenthesized. In our example, the operator with the highest precedence is the plus plus, used here as the postfix operator, so we put a parentheses around the plus plus and its operand. We now spot a prefix minus minus operator and a unary minus operator, both precedence 2 in the expression. So this one gets parentheses and this one gets parentheses. Note that the other minus sign has an operand to its immediate left, so it must be a subtraction operator, not a unary minus operator. Next, we notice the division operator, precedence 3, and wrap that whole expression or sub-expression for these two operands. The expression contains two operators with precedence 4, subtraction and addition. Whenever two operators with the same precedence are adjacent to an operand, we've got to be careful about associativity. In our example, minus and plus are both adjacent to D, so associativity rules apply. The minus and plus operators group from left to right, so parentheses go around the subtraction first, then the addition. So you would put the parentheses around here, and then around the entire thing there. The only remaining operators are equals and plus equals. Both operators are adjacent to B, so we must take associativity into account. Assignment operators group from right to left, so parentheses go around the plus equals to operator first, or sub-expression, and then around the entire expression. The expression is now fully parenthesized. Order of sub-expression evaluation. The rules of operator precedence and associativity allow us to break any C expression into sub-expressions to determine uniquely where the parentheses would go if the expression were fully parenthesized. Paradoxically, these rules don't always allow us to determine the value of the expression, which may depend on the order in which its sub-expressions are evaluated. C doesn't define the order in which sub-expressions are evaluated, with the exception of sub-expressions involving the logical and, logical or, conditional, and comma operators. Thus, in the expression parentheses a plus b close parentheses times parentheses c minus d close parentheses, we don't know whether a plus b will be evaluated before c minus d. Most expressions have the same value regardless of the order in which their sub-expressions are evaluated. However, this may not be true when a sub-expression modifies one of its operands. Consider the following example, where a equals to 5 and b equals to a plus 2 minus a equals to 1. So within this expression alone, we modify the value of a to become 1, so we don't know whether the value of a here is 1 or 5, depending on whether this sub-expression is evaluated before this sub-expression. The effect of executing the second statement is undefined. The C standard doesn't say what will happen. With most compilers, the value of C will be either 6 or 2. If the sub-expression b equals to a plus 2 is evaluated first, b is assigned to the value of 7 and c is assigned to 6. But if a is equal to 1 is evaluated first, then b is assigned to 3 and c is assigned to 2. Avoid writing expressions that access the value of a variable and also modify the variable elsewhere in the expression. The expression b equals to a plus 2 minus a equals to 1 accesses the value of a in order to compute a plus 2 and also modifies the value of a by assigning it to 1. Some compilers may produce a warning message such as operation on a may be undefined when they encounter such an expression. To prevent problems, it's a good idea to avoid using the assignment operators in sub-expressions. Instead, use a series of separate assignments. For example, the statement above could be rewritten as a equals to 5, b equals to a plus 2, a now becomes 1, c equals to b minus a. The value of c will always be 6 after these statements are executed. Beside the assignment operators, the only operators that modify their operands are increment and decrement. When using these operators, be careful that your expressions don't depend on a particular order of evaluation. In the following example, j may be assigned to one of the two values. I equals to 2, j is equal to I times I plus plus. Well, I is equal to 2 here, and I is also equal to 2 here. In this expression, it will be incremented afterwards. So will this be I is equal to, this is just to j is 4? It's natural to assume that j is assigned to the value of 4. However, the effect of executing the statement is undefined, and j could just as well be assigned to 6 instead. Here's the scenario. The second operand, the original value of I, is fetched. Then I is incremented. 2. The first operand, the new value of I, is fetched. 3. The new and old values of I are multiplied, yielding 6. Fetching a variable means to retrieve the value of the variable from memory. A later change to the variable won't affect the fetch value, which is typically stored in a special location known as a register inside the CPU. This is postfix incrementing, meaning that the plus plus comes after the I, meaning that when we fetch the value of I, it will keep the original value and then afterwards be incremented, for future use. So when we fetch it, we get the value of 2. And then it's updated to 3. And we call that 3 value when we fetch this variable here. If we were reading this from right to left, which sometimes, like it's saying, it's undefined how the compiler will, or whatever compiler you're using, will reinterpret these expressions. So 3 will be fetched here giving us 3 times the original value of 2. Now, if we were to call I again down here, I for whatever calls would be 3 unless we increment it later, right? Because it was changed here. But this is still the original value of I. Undefined behavior. According to the C standard, statements such as C equals to B equals to A plus 2 minus A equals to 1 and J equals to I times A plus plus cause undefined behavior, which is different from implementation-defined behavior. When a program ventures into the realm of undefined behavior, all bets are off. The program may behave differently when compiled with different compilers, but that's not the only thing that can happen. The program may not compile in the first place. If it compiles, it may not run, and if it does run, it may crash, behave erratically, or could produce meaningless results. In other words, undefined behavior should be avoided like the plague. 4.5. Expression statements. C has the unusual rule that any expression can be used as a statement. That is, any expression, regardless of its type or what it computes, can be turned into a statement by appending a semicolon. For example, we could turn the expression plus plus I into a statement, plus plus I, semicolon. When this statement is executed, I is first incremented, then the new value of I is fetched, as though it were to be used in an enclosing expression. However, since plus plus I isn't part of a larger expression, its value is discarded and the next statement executed. The change to I is permanent, of course. Since its value is discarded, there's little point in using an expression as a statement unless the expression has a side effect. Let's look at 3 examples. In the first example, 1 is stored into I, and then a new value of I is fetched but not used. In the second example, the value of I is fetched but not used. However, I is decremented afterwards. In the third example, the value of the expression I times j minus 1 is computed, then discarded. Since I and j aren't changed, the statement has no effect and therefore serves no purpose. A slip of the finger can easily create a do-nothing expression statement. For example, instead of entering I is equal to j, we might accidentally type I plus j. This type of error is more common than you might expect, since the equals and plus character usually occupy the same key on the keyboard. Some compilers can detect meaningless expression statements. You'll get a warning such as statement with no effect. Q&A. I noticed that C has no exponentiation operator. How can I raise a number to a power? Raising an integer to a small positive integer power is best done by repeated multiplication. I times I times I is I cubed. To raise a number to a non-integer power called the POW function. I want to apply the modulo operator to a floating point operand, but my program won't compile. What can I do? The modulo operator requires integer operands. Try the fmod function instead. Why are the rules for using the division and modulo operators with negative operands so complicated? The rules aren't as complicated as they may first appear. In both C89 and C99, the goal is to ensure that the value of A divided by B times B plus A modulo B will always be equal to A. And indeed, both standards guarantee that is this in this case, provided that the value of A divided by B is representable. The problem is that there are 2 ways for A divided by B and A modulo B to satisfy this equality if either A or B is negative. As seen in C89, where either negative 9 divided by 7 is negative 1 and negative 9 modulo 7 is negative 2, or negative 9 divided by 7 is negative 2 and negative 9 modulo 7 is 5. In the first case, negative 9 divided by 7 times 7 plus negative 9 modulo 7 has the value of negative 9. And in the second case, negative 9 divided by 7 times 7 plus negative 9 modulo 7 has the value of negative 9. But these operands or sub-expressions are different. By the time C99 rolled around, most CPUs were designed to truncate the result of division towards 0, so this was written to the standard as the only allowable outcome. If C has L values, does it also have R values? Yes, indeed. An L value is an expression that can appear on the left side of an assignment, and an R value is an expression that can appear on the right side. Thus, an R value could be a variable constant or more complex expression. In this book, as in the C standard, we'll use the term expression instead of R value. You said that V plus equals E isn't equivalent to V equals V plus E if V has a side effect. Can you explain? Evaluating V plus equals E causes V to be evaluated only once. Evaluating V equals to V plus E causes V to be evaluated twice. Any side effect caused by evaluating V will occur twice in the later case. In the following example, I is incremented only once. Why does C provide the plus plus and minus minus operators? Are they faster than other ways of incrementing and decrementing, or are they just more convenient? C inherited plus plus and minus minus from the Ken Thompson earlier B language. Thomson's apparently created these operators because his B compiler could generate a more compact translation for plus plus I rather than for I equals I plus 1. These operators have become a deeply ingrained part of C. In fact, many of C's famous idioms rely on them. With modern compilers, using plus plus and minus minus won't make a compiled program any smaller or faster. The continued popularity of these operators stems from mostly their brevity and convenience. Do plus plus and minus minus work with floats? Yes. The increment and decrement operations can be applied to floating point numbers as well as integers. In practice, however, it's fairly rare to increment or decrement a float variable. When using the post version of plus plus or minus minus, just when is the increment or decrement performed? That's an excellent question. Unfortunately, it's also a difficult one to answer. The C standard introduces the concept of sequence point and says that, quote, updating the stored value of the operand shall occur between the previous and the next sequence point. There are various kinds of sequence points in C. The end of an expression statement is one example. By the end of an expression statement, all increments and decrements within the statement must have been performed. The next statement can't begin to execute until this condition has been met. Certain operators that we'll encounter in later chapters, logical and, logical or, conditional and comma, also impose sequence points. So do function calls. The arguments in a function call must be fully evaluated before the call can be performed. If an argument happens to be an expression containing a plus plus or minus minus operator, the increment or decrement must occur before the call can take place. What do you mean when you say the value of an expression statement is discarded? By definition, an expression represents a value. If I has a value of 5, for example, then evaluating I plus 1 produces the value of 6. Let's turn I plus 1 into a statement by putting a semicolon after it. When this statement is executed, the value of I plus 1 is computed. Since we have failed to save this value or at least use it in some way, it is lost. But what about statements like I equals to 1? I don't see what is being discarded. Don't forget that equals is an operator in C and produces a value just like any other operator. The assignment, I is equal to 1, assigns 1 to I. The value of the entire expression is 1, which is discarded. Discarding the expression's value is no great loss since the reason for writing the statement in the first place was to modify I. And boom. All right, you guys, thanks so much for joining me today. That was Chapter 4, Expressions from C Programming a Modern Approach by K.N. King, 2nd edition. Thank you guys so much for being here, and I'll see you in Chapter 5 in the next one. Bye, guys.